Hello everyone. In the last class we had discussed about a canonical ensemble where we discussed that it is practical to keep T constant, and for doing that it is easy to keep the system inside an infinite capacity heat reservoir. Here the system is described by A. Er is the energy, T is the temperature, and the infinite capacity heat reservoir is E prime R and the temperature is T. We have kept the temperature T constant. Now here consider a system A inside a large heat reservoir A prime. At equilibrium both have same temperature. The individual energies are variable, and then the total energy of the composite system, that is A plus A prime, should be same. There should be constant. So Er plus Er prime is equal to E0 is equal to constant. We know the system has much less energy than the total energy. So we can write Er by E0 as in this form, that is 1 minus Er prime by E0, much less than 1. Now here the heat bath is very large and there are large number of states compatible with it. Now with energy E prime, and the number of states be denoted by omega prime Er prime. Here we know we are having there are infinite number of states possible, and they will be denoted as omega prime Er prime. Now the relevant probability PR is proportional to the number of microstates which the reservoir has, which is omega prime Er prime. The concept of microstates have been discussed in the beginning of statistical basis of thermodynamics. So I hope you will not have any issues with it. Now here the probability is proportional to omega prime Er prime, such that we can write omega prime is equal to E0 minus Er. Er prime can be written as E0 minus Er. So again PR is equal to C omega prime Er prime. So log of PR will be K plus ln omega prime Er prime. Now we need to expand. Here we are expanding it around Er prime is equal to E0. That is Er is equal to 0. So ln omega prime is equal to Er prime is expanded along Er prime is equal to E0. That is Er is equal to E0. So once you do an expansion, the expansion, that is the basic expression, is given by that when you are expanding x about it. So what will be the terms? So ln omega prime Er prime is equal to ln omega E0 plus dou of ln omega prime by dE prime. E prime is equal to E0 Er prime minus E0. Now here these things the further terms are neglected, and we know this will be a constant, and this was something which we have learned when we were discussing entropy in the beginning itself. So that is dou ln omega by dE NV is actually beta. So we will write it as, here it is omega prime, so we will write it as beta prime. Now here one thing we have realized, beta is dependent on temperature. So in equilibrium beta prime is equal to beta is equal to 1 by kT. So here PR is proportional to, we have discussed PR here. So PR is equal to proportional to exponential minus beta ER. Now when you normalize it means PR is equal to CE beta ER. So again the total probability is 1. So our final value PR is equal to exponential minus beta ER by summation over exponential minus beta ER. This is a very important term which you will be using in our further expressions. Now the physical significance of various statistical quantities. Once you have got the probability, normalized probability rather, so we know the total energy will be what? The energy of each state into the probability of its occupation and the summation over the whole region. So it will be summation R, ER, PR. So total energy, so we can write it as summation ER exponential e raised to beta ER and summation exponentials minus beta ER. This can also be written as minus d by d beta ln exponentials minus beta ER. This we can easily check. You know, when you take the exponential, it will be 1 by exponential, and into this, when you're doing it with beta, you will get an ER term, so you will get this term. But this is again a very relevant expression. Now, we know from our basic thermodynamic relations, Helmholtz energy, that is A is equal to U minus Ts. So dA is equal to du minus Tds minus SdT. Again, what is du? That is du is Tds minus Pdv. So when you substitute Tds minus Pdv, these terms go. Here we are taking U as the internal energy. Let me tell you. So here you get this expression minus s dt plus minus p dv plus mu dn. So where s, p and mu can be calculated from the Helmholtz free energy. So if we are able to get the Helmholtz free energy from this expression, then lot of parameters can be devised. So you write u is equal to a plus ts, which is a minus t dou a by dou t nv, and on analysis you will get this expression minus d dou a by t dou 1 by t nv. Now here we know beta is equal to 1 by kt. So ln exponential minus beta by er actually uh, is minus a by kt. So from these expressions we realize that u that ln epsilon summation r exponentials minus beta er is minus a by kt because of this relationship. Now here, so a nvt is actually minus kt ln qn. Now what is this qn? Qn we will realize qn is the partition function. So qn is actually exponential minus er by kt, exponential minus er by kt summation over r. So that is the sum of states of the factor e raised to minus beta er. Beta is actually 1 by kt. So from all these expressions, beta is equal to minus a by kt. So a is equal to minus kt. So and from this ln br is, so this is the kt is beta. So minus a by beta, and we get this expression. Now this is a very important thing, that is the partition function. Now here when we look, we know a is an extensive quantity and the partition function also must be an extensive quantity because again it is associated with it directly. Now with this we will move to derive certain basic thermodynamic quantities. Since a is known, that is Helmholtz energy is known, other quantities can be derived. So here Cu, Cv can be derived. G is what? A plus Pv. So Gv can be derived. Again we know P. P is minus dou A by dou V and T. So again A is minus KT ln QVT. So when you do for P, because you are deriving it with respect to V, so this term will also only appear. So this term on differentiation you will get, because it is ln Qn, so Qn goes to the denominator, into minus 1 by kt, expand Qn, you will get this expression. So finally the pressure expression comes out to be minus summation r dou er by v exponentials minus beta er summation exponential minus beta er. Again, once again let me tell you, beta is equal to 1 by kt. Sometimes we are using by kt, sometimes we are writing beta. Now this beta, we know summation beta. So now what is this? This term is actually the probability. So pressure can be written as PR probability into dou er by dou v. Now see this part. If you look at this part, exponential minus beta er by summation exponential minus beta is nothing but the probability. So P can be written as PR dou er by dou v. So now PdV, take dV. So PdV can be written as minus summation r PR dEr, which is also equal to minus du. From equation 1, in equation 1 we had said PR ER is equal to U, so PR dEr is equal to minus du. Now here again let me look here. So what is again probability? Probability is Q inverse exponentials minus beta er. We know this is probability. Exponential minus beta er by summation exponential minus beta. Whereas my exponential minus beta er is actually the partition function. So summation, so the probability can be given as Q inverse. So it is 1 by, so this is Q inverse exponential minus beta er. So ln of PR, so this is the mean value, ln of PR can be written as, you try to apply logarithm here, minus log Q minus beta, the summation ER. We know of this relation A plus TS is equal to U also, and we apply here, which is equal to beta A minus U, which is equal to beta A minus Ts. So ln of PR is actually coming out to be 1 by kt minus Ts, or is equal to minus S by K. Now what is this S by K? S by K can be written as S is the entropy. So entropy can be written as minus K. Now mean value ln PR. When you take the mean value, the meaning is if it is a function, then it is summation the function e minus beta e by e minus beta e. That is the probability. So this can be written as, this whole term can be written as in this form. So this is PR and this is ln PR. So this comes out to be summation PR ln PR. Now this term is very relevant from our knowledge of many basic thermodynamic laws, because here you see the entropy of a physical system is solely determined by its probability values. So S is minus K summation R PR ln PR. Now here what happens, if you look carefully, see when the temperature is 0 Kelvin, the system, the particles, they cease to move and they remain in a constant phase. So here they remain in a single phase. Since there is no random movement, and if the system, all the particles of the system is in ground state, then the probability of finding a state is PR is equal to 1 in ground state, and for all other states PR is 0. So then entropy becomes 0. Otherwise, so now here what is it? This condition, that is S is equal to 0 for PR is equal to 1, and S is equal to 0 for PR is equal to 0. For all other states PR is equal to 0. So if you put PR is equal to 1 for ground state or PR is equal to 0 for other states, entropy is 0, which is nothing but our third law of thermodynamics, which says the entropy of a system at 0 Kelvin is 0. So here the entropy of the system at T is equal to 0. Okay, it defines the Nernst heat theorem or the third law of thermodynamics, as depends on the number of accessible states and therefore PR. And when the number of states is large, as increases, leading to statistical disorder. Okay, this is also very clear because it depends on the probabilities. So here, when the more number of states are equally accessible, then what will be happen? There will be more disorder as the temperature increases. So this is from here, from this derivation, we have even derived or at least validated our third law of thermodynamics. So that's it. Thank you.